Imagine a metal plate exposed to a constant heat source. Eventually, the temperature stops changing and settles into a perfectly balanced, steady-state equilibrium. Systems like this, which lack internal heat sources or sinks, are strictly governed by the 2D Laplace equation. This schematic defines our physical problem space. We have a square domain with unknown interior values, but locked outer boundaries. These represent Dirichlet conditions. The left, top, and bottom walls are held at 0, while the right edge is driven by a continuous sine wave function. In reality, there are infinite points inside this square. Calculating exact potential for infinite coordinates is physically impossible for any computer to process. To simulate this partial differential equation, we have to make a mathematical compromise. We must overlay a finite, calculable grid across that continuous physical space. This diagram illustrates that discretization. We take both the x and y axes and break them down into exactly 50 distinct segments. Using Python, we execute this geometry programmatically by generating evenly spaced coordinate arrays for the length of each axis. This creates uniform gaps between our newly formed points, defined as the horizontal and vertical distances dx and dy. Setting n to 50 is a deliberate choice. It balances high numerical accuracy of the physics with manageable computational cost for our computer's memory. Through this structural limitation, we have successfully translated an infinite physical domain into a clean grid of exactly 2,500 programmable nodes. We immediately face a linear algebra bottleneck. Traditional matrix solvers process data as flat, one-dimensional vectors, but our physical problem exists in 2 dimensions. We must flatten the spatial coordinates. Every point from the square grid has to be uncoiled and lined up into a single massive sequence. We handle this translation using a specific indexing equation, k equals I plus j times n. Here, I and j represent the original column and row coordinates of any given point on the grid. By multiplying the row index j by the total grid width n, the equation skips precisely the right amount of memory slots to maintain the true vertical relationships between points. Applying this logic, the node at position 0, 0 becomes index 0 in our vector, while a node at position 2, 2 drops down to index 8. This mapping rule forces one-dimensional computer memory to respect two-dimensional topological relationships, keeping the physics intact throughout the calculation. Now we can determine the physical behavior of the grid by isolating a single interior point. This graphic shows the 5-point stencil. We approximate continuous partial derivatives using central differences, calculating forces from the north, south, east, and west neighbors. The Laplace equation dictates harmonic averaging. The central point's potential is perfectly balanced by the average of these 4 surrounding nodes. To make this computable, we must map these local relationships into a giant global system matrix, which we call A. This slide illustrates the translation. The horizontal x derivative is broken apart and assigned as matrix coefficients based on 1 over dx squared. The vertical y derivative translates identically, populating the matrix with coefficients based on 1 over dy squared. To complete the balance, the central point absorbs the negative sum of all 4 surrounding weights, placing our -2 factor directly on the matrix diagonal. The continuous physics of the original equation have now been explicitly hard-coded as structural rules inside matrix A. There is one strict exception to this rule. Boundary points do not perform harmonic averaging. We already know their absolute physical values. To lock these known values into the linear system, we utilize an identity matrix structure. By setting the central diagonal element to exactly 1 and forcing all neighboring connections to 0, the math guarantees that 1 times our node simply equals the exact target value in our solution vector B. Programmatically, we apply this rule to the left, top, and bottom edges of our grid, assigning them a hard 0. But for the right edge, we explicitly feed the target vector the output of our sine wave function. We aren't asking the computer to solve for these boundaries. They are the immovable anchors supplying the energy that drives the rest of the simulation. Scaling this up to our n equals 50 grid means matrix A expands into a massive 2,500 by 2,500 structure. This plot visualizes the data. Because the 5-point stencil connects a node to its 4 neighbors, the matrix is mostly empty, filled with zeros. Storing this crashes memory. We avoid this by converting to compressed sparse row format, discarding zeros and optimizing computation. Our physical simulation is now distilled into a single linear system. A times phi equals B. A holds the interior rules, and B holds the boundary fuel. We pass this sparse system to the linear solver to generate the phi vector. In mere milliseconds, that single computational command simultaneously balances all 2,500 individual equations, locking them in to find the exact numerical steady-state equilibrium. The solver returns the phi array, which is a flat, one-dimensional list of 2,500 numbers. A flat sequence of data cannot visually represent a two-dimensional physical surface. We have to reconstruct the original geometry. We do this by taking our initial flattening formula and running it backward. Python executes this topological reassembly entirely through the reshape command, folding the data back into an n by n block. The success of this single operation proves that our uncoiling algorithm successfully maintained the topological relationships of the grid during computation. We can now plot this restored spatial data over our original x and y coordinate grid. Notice the transpose operation in the rendering code. This is a critical edge case that physically aligns the array's orientation with the spatial axes of the plot. This beautiful contour map is the resulting physical simulation. Look at the right edge. You can clearly identify the concentrated high-potential region being pushed into the system by our fixed sine wave. From there, the gradient diffuses smoothly across the interior domain, steadily losing energy until it reaches the zero potential walls on the other three sides. The visual output validates the entire numerical approach. There are no sudden artifacts or sharp jumps. The energy simply diffuses, exactly as Laplace's law requires. This final summary diagram outlines the full numerical pipeline we successfully constructed. We took a continuous mathematical concept, discretized it into strict local logic, assembled a massive sparse data engine, and calculated the physical pixels. Effective numerical modeling translates elegant mathematics into efficient computational logic, overcoming the physical impossibility of continuous calculation.